Welcome to this brown bag deep dive into the architectural history and mathematical data models of Git. Today, you will learn the precise technical reasons why Git replaced centralized version control systems, how its content-addressable directed Acyclic graph operates under the hood, and how it handles extreme scaling via Reftables and Packfiles.
Let's jump right into part 1, the snapshot model versus legacy Delta storage. To understand the architectural decisions behind Git, you first have to understand the specific engineering crisis that forced its creation. Between 1991 and 2002, the Linux kernel project relied heavily on manual patch integration. Patches were passed around via mailing lists and tarballs.
Which was highly inefficient for a project of that absolute magnitude.
Right. So in 2002, the community adopted BitKeeper, a proprietary distributed version control system developed by Larry McVoy.
But using proprietary software for an open-source project created persistent ideological tension within the community. In April 2005, this tension culminated when Bitmover, the company behind BitKeeper, revoked the free-of-charge license for kernel developers.
The catalyst for this revocation was Andrew Tridgell's creation of SourcePuller. He utilized a standard telnet connection to reverse engineer the BitKeeper protocol, which violated the terms of service,
leaving Linus Torvalds requiring an immediate replacement to maintain the kernel's development velocity.
Exactly. Existing systems at the time, specifically the Concurrent Version System, or CVS, and Subversion, or SVN, possessed systemic architectural flaws that disqualified them from managing the Linux kernel.
Torvalds initiated Git development on April 3, 2005. He intentionally designed an architecture that operated as the exact opposite of CVS. The development speed was remarkable. By April 7, Git was self-hosting its own code, and by April 18, it successfully supported its first multi-branch merge.
The fundamental flaw in legacy systems was their strict reliance on file-centric tracking and delta-based storage. CVS and SVN tracked individual files and stored repository history as a sequence of edits, commonly known as deltas.
Subversion marketed itself heavily as CVS done right by introducing atomic commits. However, it retained a centralized server architecture, creating a major single point of failure.
And more critically, its delta-based storage severely degraded performance at scale. If we examine the mathematical model of delta storage, the computation problem becomes obvious.
As the formula on screen demonstrates, calculating the state of a repository at snapshot n requires taking the initial state and summing all deltas. Mathematically, S sub n equals S sub 0 plus the sum of delta I from I equals 1 to n.
This mathematical reality means historical reconstruction becomes exponentially more expensive computationally as the repository grows. Git fundamentally rejects this paradigm.
Instead, Git stores complete, independent snapshots of the entire project.
When you retrieve the state of a project at day 6, Git does not calculate anything. It reads the snapshot for day 6 directly from the database. Differences are computed on the fly only when you explicitly request a diff operation.
Torvalds prioritized compute time over disk space, leveraging his deep expertise in operating file system performance to optimize for the massive code base of the Linux kernel. Which brings us directly to part 2, the content-addressable object store and Merkle trees.
The core implementation lives entirely in the hidden .git/objects directory. Git does not track file names in the way a user thinks about them. It tracks content mathematically using a strict key-value store.
During the initial design phase, Torvalds evaluated Monotone, a contemporary system that utilized cryptographic naming for its data. Monotone correctly prioritized data integrity, but it lacked the disk throughput required for the Linux kernel scale.
So Torvalds instead engineered a system mirroring a traditional file system, but located entirely within that object's directory. The key in this store is a 160-bit SHA-1 hash of the content itself.
This is the exact definition of content-addressable storage. Data is handled strictly based on its mathematical identity, not its location or name.
The precise implementation pattern operates at the C level as follows. Git takes the literal string blob, adds a space character, appends the exact file size in bytes, inserts a null byte to act as a delimiter, and finally appends the raw file content.
That exact concatenated string is then processed through the SHA-1 cryptographic algorithm. The result is a 40-character hexadecimal string.
Because it relies on cryptographic hashing if a single bit of the file changes.
The resulting hash changes entirely.
Yes. This generates a completely new, isolated object in the database. However, Storing millions of flat files in a single directory heavily degrades standard operating system file system performance.
To mitigate this, Git implements a highly effective prefix routing optimization. The first 2 characters of that resulting hash become the directory name, and the remaining 38 characters become the file name.
This ensures rapid I/O operations by preventing directory index overloading at the operating system level. Git then organizes these isolated, nameless blobs into a cohesive project hierarchy using Merkle trees.
In a Merkle tree, leaf nodes are cryptographic hashes of data, and internal nodes are hashes of their respective children.
Git constructs this tree utilizing 4 primary object types. First, blobs contain the compressed raw data without any file names attached. Second, trees represent directory snapshots. Trees store lists of tuples containing the file mode, the file name, and the SHA-1 pointers to the corresponding blobs or nested trees.
Third, commits represent specific historical snapshots. A commit object contains the top-level tree hash, the parent commit hashers, and essential metadata like the author and timestamp.
And finally, tags operate as immutable pointers to specific commits. The parent-child linkage between these commit objects forms a directed acyclic graph, commonly referred to as a DAG.
Because every commit hash explicitly incorporates the hash of its parent commit, the entire repository history is cryptographically immutable.
Any modification to historical data, even changing a single character in a commit message from 3 years ago, fundamentally alters the hash of that commit,
which instantly invalidates every subsequent node in the graph, requiring a complete rewrite of the downstream history. This architecture guarantees the absolute data integrity that centralized systems failed to provide.
Torvalds stated that SHA-1 was chosen primarily for this data integrity, specifically the ability to trust data against hardware failure and accidental disk corruption.
Let's transition to part 3, plumbing, Porcelain, and the index. Developers do not interact with these hashes manually. Git's initial release was simply a collection of low-level, shell-scriptable tools known internally as plumbing.
The high-level commands you use daily in your development environment, such as git commit or git add, are Porcelain commands. They are built purely as wrappers around those underlying plumbing primitives.
This specific toolkit design exposes the underlying mathematical data model directly to the user. The most critical and often most misunderstood component of this exposed interface is the index.
The index, which is referred to internally in the Git source code as the Dircache, serves as a mandatory intermediate staging area between your working directory and the directed acyclic graph.
Physically, it is a binary file located at .git/index. If you inspect the file header, it begins with the magic number DIRC,
followed immediately by a version number and a direct count of the entries it contains. This specific binary structure has remained remarkably stable since 2005. The index performs 3 essential functions for the version control workflow. First, it enables incremental staging,
allowing engineers to build highly atomic commits by staging specific file modifications without committing the entire working directory.
Second, it operates as a sophisticated performance cache. By saving critical metadata like file timestamps and file sizes, Git completely bypasses the need to read full file contents from the disk just to detect modifications.
Third, and perhaps most critically for collaborative environments, it drives merge resolution. During a complex merge operation, the index is capable of storing multiple versions of a single file simultaneously.
It explicitly holds the common ancestor version, the local version, and the remote version all at once. This specific capability is what powers Git's 3-way merge logic.
Understanding the index is critical for avoiding common engineering failure modes. The confusing behaviors engineers experience with Porcelain commands directly result from manipulating this exposed state.
A primary example is the git reset command. The confusion occurs because git reset simultaneously manipulates 3 distinct states: the head pointer, the index, and the working directory.
When you execute these commands without fully understanding the discrete states of the working tree versus the index, unrecoverable data loss occurs. You have to adopt the system's mental model.
Academic modeling of Git defines it precisely as a persistent, purely functional data structure. This takes us into part 4, structural sharing and scale optimizations.
The computer scientist Chris Okazaki defines persistent data structures as those where previous versions remain entirely accessible and unmodified after updates occur.
Git's inherent immutability ensures updates strictly create new nodes in the DAG, never mutating existing nodes. Git exhibits a property called confluent persistence, allowing distinct versions of the data structure to merge into a completely new version.
The operational efficiency of this model relies entirely on structural sharing. Structural sharing actively prevents data duplication across snapshots.
If two historical snapshots differ by exactly one file, they share the identical tree and blob objects for all unchanged directory paths.
To put that in concrete terms, consider a project containing 10,000 files. If an engineer modifies a single file deep within a nested directory structure, Git does not duplicate the remaining 9,999 files.
It generates exactly one new blob object for the changed file. It then generates new tree objects, specifically D-new trees, where D is the depth of that file in the directory hierarchy. Finally, it generates one new commit object pointing to the new top-level tree.
As shown in the structural diagram on screen, this results in an operational cost of big O of D log n. This highly efficient logarithmic overhead allows Git to store millions of commits effortlessly.
But even with structural sharing, managing physical disk scale requires further optimization. To prevent loose object bloat, Git implements Packfiles.
When the git gc, or garbage collection, command executes, Git triggers storage-level delta compression.
It bundles thousands of individual loose objects into a single, highly compressed pack file. Inside this pack file, it stores base blobs and calculates deltas for similar files.
This internal optimization strictly operates at the storage layer. The logical model presented to the user continues to represent full, independent snapshots.
Modern enterprise repositories introduce extreme scaling demands, particularly concerning reference updates. Storing branches as flat files in the legacy packed ref system created severe file system lock contention.
This failure mode was particularly visible in CI/CD environments managing hundreds of thousands of concurrent branches. So in 2024, Git integrated the Reftables backend to solve this exact limitation.
Reftables utilize a specialized binary format that enables atomic writes and constant time lookups. The table on screen compares legacy packed refs to the new binary Reftal format in cold cache scenarios. Scanning drops from 402 milliseconds to 112 milliseconds.
Lookup by name drops from roughly 409,000 microseconds to under 34 microseconds. This is a massive improvement.
Alongside reference scaling, the most complex architectural shift Git faces today is the ongoing transition from SHA-1 to SHA-256. Cryptographic research demonstrated viable collision attacks against SHA-1.
Because the hash operates as the fundamental identifier for absolutely every object in the database, modifying the hash function impacts the entire codebase. The technical transition plan is structured to avoid a flag day where all systems must update simultaneously.
Reference the transition plan table on screen. It outlines 4 distinct operational modes. It begins with dark launch for internal logic testing. This is followed by early transition to ensure legacy interoperability.
Then late transition handles migrating defaults across systems. Finally, post-transition removes the legacy SHA-1 logic entirely.
Throughout this extended process, Git maintains a sophisticated bidirectional mapping mechanism, ensuring that local SHA-256 repositories synchronize perfectly with legacy SHA-1 remotes.
Let's apply these architectural facts to daily decisions in Part 5. Engineering workflows and pitfalls. A frequent pitfall is demanding explicit rename tracking from the system.
Legacy source control management systems record file renames as explicit metadata within the database. Engineers repeatedly propose adding explicit rename logs to Git commit objects.
Linus Torvalds deliberately rejected these proposals, famously labeling them track files crap. Git operates on a stupid content tracker philosophy.
It tracks mathematical content, not file identities. Git detects renames heuristically at the computation layer during the diff phase. It compares the similarity of blobs across 2 different trees.
If a file is moved and slightly modified, the similarity heuristic successfully identifies the rename. To avoid breaking your repository history, do not rely on explicit rename logs.
You have to understand that moving and heavily modifying a file simultaneously may break that similarity heuristic. The architectural goal is to keep the underlying data model as simple as possible.
The initial choice of storage backend also dictates current debugging protocols. During initial development, the community debated utilizing traditional relational databases, like Berkeley DB, for the object store.
Torvalds rejected monolithic databases in favor of the flat file system. A monolithic database represents a severe single point of failure. If the database file corrupts, the entire repository is destroyed.
By exposing objects as flat files, Git successfully isolates corruption. If a single object corrupts in your objects directory, the rest of the repository survives.
And standard Unix tools can inspect the remaining hashes. This specific simplicity enabled the development of alternative implementations like libgit2 and jgit, which power the IDE and hosting ecosystems today.
The decentralized architecture effectively democratized software development, directly enabling platforms like GitHub and GitLab. We will close this session with exactly 3 concrete action items for you to execute this week to reinforce these concepts. First, run a plumbing command like git catfile-p on a known hash to inspect the raw blob or tree header and see the underlying data structure firsthand.
Second, navigate into your .git/objects directory to visually verify the 2-character prefix routing system functioning on your own operating system.
Third, audit your CI/CD pipeline's fetch times and evaluate if enabling the Reftable backend would optimize your automated workflows, especially if you have a monorepo with high branch churn. If this technical breakdown was valuable, leave your questions in the comments below and subscribe to the channel for more engineering brown bag sessions.
If Git is fundamentally a purely functional data structure utilizing Confluent persistence, ask yourself, how might this exact content-addressable Merkle Tree architecture be applied beyond version control to solve current bottlenecks in global distributed databases or immutable package management?